Hi everybody, I just wanted to do a quick video to follow up to the derivations we just did where we can use them in an actual example. So pause the video for a minute and read the example text that I have up here so you understand the problem we're trying to solve. All right, so in this problem you're driving, and let's highlight the important information here. You're driving at 16 meters per second. You see a stop sign in front of you here, and you say, boy, I have to stop. In between thinking to stop and actually hitting the brakes, your reaction time creates a little delay. So for 0.2 seconds, you keep going at your original speed. At that point, you actually do press the brakes, and you begin to decelerate at a rate of about half a meter per second squared. You're told that the stop sign is 30 meters away, and you want to know if you stop in time. So we have a lot of stuff to go here. I first want to talk about this 30 meters. This 30 meters is an interesting thing because it's not really a value that you necessarily want to use in this problem. It's what I like to call a comparison value. You actually have all this information. You want to figure out how long it takes you to stop, and then you want to compare it to that 30 meters, and you want to see, did I stop in time or not? So not every bit of information you're given in the problem actually goes into the equations. Sometimes you have to use it to make sense of the answer at the end. Okay, so I've drawn a little motion diagram here, and I just want to go through the elements of how I chose to diagram out this problem. So first of all, I drew a little coordinate system. I said the origin is where I'm starting. After 0.2 seconds, and I'm starting with a velocity of 16 meters per second, with no acceleration, because remember in that first part, I'm not doing anything, even though I think I am. My foot is just hovering in midair while my brain is communicating to it to push the gas, to push the brake pedal. So I'm still at a speed of 16 meters per second after that, at an unknown position x1. So we don't know actually how far I travel in that time between thinking to stop and actually pushing the brakes. I've also indicated that by a few equally spaced little dots in a motion diagram. Remember, when dots are equally spaced, it means that you're traveling at a constant speed. At x1, I suddenly do hit the brakes. I'm still traveling at 16 meters per second, and you can see here now my dots start to get closer together, indicating that I'm slowing down. I just drew them, however, I didn't calculate anything. It was just meant to represent the idea of slowing down. I put the rate at which I'm slowing down, which we know is 5 meters per second squared, and I added a negative sign because I defined the positive direction as forwards, or as to the right. And since my velocity is positive, I know I'm slowing down if my acceleration and velocity have opposite signs, so my acceleration must be negative. My final velocity is 0 at location x2. So that's the whole problem, and I don't know the time for the second part of the trip. So if we think about this as two phases, we have phase 1, where the acceleration is 0, and then we have phase 2, where the acceleration is negative 5 meters per second squared. What's important in using these kinematics equations is that when your acceleration changes in the problem, you can't just treat it as one thing. You have to phase it into different parts, so your equations are using the acceleration that goes with that part of the trip. So we're going to have to treat this trip in two different steps because there's two different accelerations. Let's start with phase 1. Since I want my strategy is to figure out ultimately x2, which is measured relative to the origin here, x1, I just want to get x2 and I want to compare it to 30 meters, and hopefully it's less than or equal to 30 meters. But in order to get x2, I'm going to need to also figure out x1. So let's start with figuring x1. So to figure out x1, let's see what I have. I know my v initial is 16 meters per second. I know my v final is 16 meters per second. I know my acceleration is 0. I know my time is 0.2 seconds. I know my x initial is 0, and I want my x final, which I'm calling x1. Well, with all of that, and having 0 acceleration simplifies the equations considerably. When I look back at my equations, I want to have one that has x, that has t, that has v initial, and so the one I want to use is this one here. without v final, just because there's a number of that I can use, but I'm going to use that one. So using that equation for phase one, I do x final, which is what I want to know, equals x initial, which is 0, plus v initial times t, plus 1/2 at squared, but a is 0, so that whole term goes to 0. And so that was pretty straightforward. I get that x1 is 3.2 meters. And I'm going to keep that in my pocket just because I'm going to need to use it as the starting point for phase 2 in order to get x2. So now let's move to phase 2. That was phase 1. Now we'll do phase 2. Let's write out the same thing. For phase 2, I'll do it in blue. My v initial is 16 meters per second. My v final, that was v initial, v final is 0. My acceleration is negative 5 meters per second squared because it's opposite my velocity, so it's negative. I don't know my time, and I don't care about my time. No one's asking about that. I know v final, v initial. I know my x initial is 3.2 meters, and I know my x final. I don't know my x final. It's x2, and I want to get that. That's what I want. So I want to get x. I have all this information, but I don't have time. And so that's where this third equation really comes in handy, because it just doesn't have time involved, and I don't want to have to stop, figure out time, and then plug it in. I could do that. It would just add a few extra steps that I don't want to waste my time doing. So let's use that equation. V final squared equals v initial squared plus 2a x final minus x initial. Well, my v final squared is 0 squared. My v initial squared is 16 meters per second squared plus 2a, and then x2 minus 3.2. I'll squeeze it in there. So now if I work that all out and solve that for x2, and you can pause the video and do that to make sure you do it correctly, I get x2 equals 28.8 meters. And remember, that is measured relative to the original origin, so I don't need to add anything to it. If I had made, I just want to back up, if I had made over here my x initial 0, if I had like reset the 0 for the second phase of the problem, I would have gotten a smaller number, and then I would have needed to add it back on to 3.2 to get that 28.8. And now my final step is the comparison step. 28.8 meters is less than 30 meters, so yes, I stop on time, and that is good.